In this video, we're going to go through free energy of dissolution. Well, let's start with the obvious question. What is free energy of dissolution? So this refers to a change in Gibbs free energy, which is delta G, when a solute dissolves in a solvent to form a solution. So in this lesson, we're going to go through a lot of terms that you've probably heard before, but this is a good review for the AP test. So enthalpy, delta H, is the total heat content of a system. When delta H is positive, that represents an endothermic reaction, so energy is being absorbed. A negative delta H value is exothermic, which means energy is being released from the system, and that is the favored value for enthalpy. So when delta H is negative, it's exothermic, that is thermodynamically favored. Entropy, or delta S, is the disorder or randomness of the energy in a system. A positive delta S means increasing disorder, which is thermodynamically favored. Negative delta S is decreasing disorder. So with entropy, more disorder would be more moles of something. They're moving faster. That's positive entropy. Okay, so when a solution is formed, there are three processes that occur. So the intermolecular forces between solvent particles are overcome, meaning they can break apart. IMF between solute particles are overcome, meaning they break apart. In order to break bonds, you have to absorb energy. So that's why our delta H value is positive here. Since there are more particles when intermolecular forces are overcome, so they're breaking apart essentially, we have a positive delta S, or positive entropy value. Now, when particles reform, energy is released, hence the negative value for delta H here. And when particles reform, you're ending up with fewer particles floating around, less disorder, which makes our delta S value, our entropy value, negative. Okay, so now let's dig into Gibbs free energy and how this relates to dissolution. So here's the equation for Gibbs free energy. So you're going to take your enthalpy value, which is delta H, you're going to subtract the temperature multiplied by your entropy value. And remember, your temperature must be in Kelvin. So Gibbs free energy is used to predict the solubility of substances under various conditions. So if your delta G value is negative, that's a spontaneous reaction and it proceeds forward under the given conditions. If your delta G value is positive, it is non-spontaneous. So it's not going to happen without a little bit of a push. So it needs external energy to happen. If delta G is equal to 0, the system is at equilibrium and there's no net change in reaction rates over time. For dissolution to be spontaneous, again, delta G must be negative. Now, the spontaneity of dissolution can depend on temperature. For example, if you have an endothermic reaction, so you're going to have a positive delta H value, it might become spontaneous at higher temperatures. And let me show you what I mean. So here's your equation, delta G equals delta H. So let's assume that this is a positive value. And then we're going to subtract temperature minus our entropy multiplied by the temperature. So if our temperature is a really high value, I'm subtracting a really big number, potentially, and our overall value, our Gibbs value, is going to be negative. So if I have a smaller delta H value, and I have a really big temperature, I'll end up with a net negative here. Okay. All right, so let's look at an example. It says which solution would have greater entropy with all other factors remaining equal, and justify your answer. So we have cobalt hydroxide and beryllium hydroxide, and our KSP values are listed for both. So really all we have to go off here are the KSP values. Now, This is a good opportunity to revisit exponents. So if you have something times 10 to a negative exponent, that is a really small number. So looking at these two values here, you have negative 15, negative 22. Negative 22 might appear like it's a bigger number, but remember it's negative, so it's going to be a really small number. Okay, a lot of it's going to be a decimal, and it's going to be really, 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 really tiny. Okay, so our cobalt hydroxide has a higher KSP value, so that means that it's going to disassociate into a greater number of ions because of the higher KSP values here. Okay. So when we talk about entropy, remember, is disorder. So if it's going to dissolve more, because it has a higher KSP value, there's going to be more ions floating around. So it's going to have a greater entropy value, okay, than our beryllium hydroxide, which is a smaller KSP value. Okay, so more ions floating around means more entropy. All right, let's look at number 2. Number 2 says, consider the dissolution of a salt in water under constant pressure at 298 Kelvin. The enthalpy change of the system is observed to be 5,000 joules per mole, and the entropy change for the system is 20,000 joules over moles times Kelvin. Determine whether the dissolution of the salt is spontaneous under these conditions. So let's rewrite the equation. So delta G equals delta H minus T delta S. Okay. Now all of our units are the same here, so we've got joules and not kilojoules. We're not mixing and matching. Our temperature's already converted to Kelvin, so we don't need to convert anything, but that would be your first step if it weren't. So let's plug in our values. So our enthalpy is 5,000. Our temperature is 298. And then our entropy is 20. So when I do the math here, I end up with a value of negative 960 joules. Okay? Because our value is negative, the dissolution of salt in water is going to be a spontaneous process. And that's pretty much all you need to know about free energy of dissolution.